Okay, in this lecture, we're going to talk about mathematics and physics. So basically, we're going to talk about significant digits, scientific notation, we'll talk about dimensional analysis, and we'll also talk about writing or doing unit analysis, dimensional analysis, and also conversions. Okay, so when we talk about significant digits, we need to talk about it in terms of what they are. The only reason we have significant digits is because we have uncertainty in measurements. So let's talk about that. When you take a measurement of a length with a metric ruler, we can measure all the way to a millimeter. But what if what we're measuring falls in between those two little lines that indicate a millimeter? Then what is it? Is it 15 millimeters or is it 16 millimeters? It's neither. It's actually somewhere in between. And so what we've been taught to do is we've been taught to make a guess as to where we think that length falls. Is it 16 or 15.5? Is it 15.7? Is it 15.3? We make a guess as to what that number is going to be, even though we don't actually have it on the measuring device. When we make that guess, we call it uncertainty. That number is still significant. It's still something that we've guessed at as a measurement, but we can't have anything beyond that. We can't get a precision any better than that because that's the best that we can measure. So when you take two numbers that have guesses at the end and you multiply them or divide them or add them and subtract them, then what happens is we have to be careful where that uncertainty is in the number to make sure that we don't have more uncertainty than just one digit. Because when you're making your guess, you're only guessing one digit. So, significant digits are for measured numbers only. If you didn't measure it, or if it hasn't been measured for you, it's not a significant digit. If it's a constant, it's a constant and it wasn't measured. That means you don't have to worry about significant digits when multiplying by constants. So this is where it gets a little tricky. Everybody wants to use every number that they put into a formula for significant digits. It really makes it easy, doesn't it? If we just use every number. Unfortunately, we can't do that. For instance, the magnitude of the acceleration due to gravity is 9.8 meters per second squared. That 9.8 is a constant that we use for most of our calculations, and therefore we can't use it towards significant digits. What if I have a formula that has a 1/2 or a 2? That's a constant. Now what if I have counted numbers? In other words, I made the measurement 10 times or 20 times. You're not going to count that either. It's not actually a measured number that you have uncertainty with. You know for sure that you've counted 5 or 10 or 20 or even 50 times. So counted numbers also do not count towards significant digits. There are 3 rules when we talk about significant digits. The first rule is that all non-zero numbers are significant. That means if I measure a number that's 562, it will have 3 significant digits, because the 5, the 6, and the 2 are non-zero numbers. If I have a final 0 or a couple of zeros after the decimal point, they are considered significant. So if I measure a number 5.00, those 2 final zeros after the decimal point are significant. Any zeros in between 2 significant digits are considered significant. So what does this leave us with? It means that zeros that are there for placement purposes only are not considered significant. This is usually called the 4th rule. But if you look at the other 3, if it doesn't follow those 3, then that means it's not significant. So you really only need these 3 rules right here. Okay, so let's practice. What I want you to do is make sure that you're looking at the previous slide, and let's go ahead and look at this, or at least on yours, make sure you're looking at your lecture notes. Okay, so 6,809. How many significant digits does it have? Hopefully you chose 4. Now you may be thinking, wait a minute, why is it 4? Well, you have 3 digits that are non-zero. You don't have any final zeros after the decimal place, but you do have a 0 in between the 8 and the 9, which are significant digits. That means that you have 4 significant digits. Okay, let's look at number 2, 0.00354. If you wrote down 3 significant digits, you are correct. Now you may be thinking, well, wait a minute, those 2 zeros are after the decimal place. Why don't they count? Well, they're not final zeros. A final 0 has to be at the end of the number. So if this had been 0.35400, then of course those 2 zeros would be significant. In this case, though, we have 3 digits that are non-zero. We have none that are zeros in between those numbers, and we have no final zeros after the decimal place. That leaves us with 3 significant digits. Okay, take a look at number 3. In number 3, we have 1 significant digit. All of those zeros fall without a decimal point. They are for placement purposes, and therefore we have 1 significant digit. For number 4, we have 2.00 times 10 to the 2. Hopefully you're getting the hang of this now, and there should be 3 significant digits written down. Notice the 2 is a non-zero number. This 0 is a final 0 after the decimal point. This 0 is in between 2 significant digits. That gives us 3 significant digits. Actually, I should be writing this down. So this is 4, this is 3, this is 1, this is 3. Now notice here, we have 200. How many sig figs is that? That's right, if you chose 1 sig fig. Remember, these 2 zeros here are for placement purposes only. Notice the difference between 4 and 5. It's exactly the same number. But notice that for number 4, we've written it in scientific notation. That tells us that those 2 zeros have been measured and that they are significant. Whereas in number 5, this is actually your guess, this number 2. Okay, look at number 6, 0.000100. How many sig figs is that? That's right, it's 3 significant digits. We have the 1, which is a non-zero digit. That's a significant digit. We have this 0, which is a final 0 after the decimal place. And we have this 0, which falls in between 2 significant digits. That gives us 3 significant digits. We could also write this number as 1.00 times 10 to the minus 4. And that would definitely tell us that those 2 zeros are significant. Okay, so now what we're going to do is we're going to talk about adding and subtracting numbers that have significant digits. We're going to be looking at the precision. What does that mean? It means we're looking at how many digits follow the decimal point. So if I have a number that has 3 digits after the decimal point, and I have another number that has 2 digits after the decimal point, we want the number that has the least number. So we would choose 2, and that's how many we have to have after the decimal point in our answer. This gets tricky, because a lot of times you want to say, well, I started out with 2 sig figs, I need to end with 2 sig figs. But it doesn't work that way. You could actually end up with more significant digits by adding or subtracting than you can by multiplying and dividing. Okay, so be careful. It's the precision that matters, not what goes in front of the decimal point. But what does that mean about decimal point? It means you have to have one. So if I write the number 1,000, does that have a decimal point? No, I have to give it one. So let's go ahead and take a look at this. Okay, so I have the number 9.00, and I'm going to add it to 5.4. Now, what I'm going to do is I'm going to go ahead and circle the uncertain digit. This is my guess. And this is my guess. It's always the last number. Okay, so now what I'm going to do is I'm going to add these two numbers together. And I'm going to continue to circle the uncertain digits. So this 0 is uncertain because it comes from this 0. And this 4 is uncertain because this 4 is uncertain here. How many uncertain digits can I have in a measurement? That's right, only one. So this 0 has to go away, and that means that my answer has to be 14.4. Now let's see if this follows the rule of precision. How many digits after the decimal place do I have here? 2. How many do I have here? 1. So that means my answer has to have one digit after the decimal place. Is that the case? Yes, it is. Now you may be saying, well, wait a minute though, this 5.4 only has 2 sig figs. My answer has 3. That's not right. Again, remember I told you, it doesn't matter what goes in front of the decimal point. What matters is what is at the end of the decimal point. So now what we're going to do is we're going to do a subtraction problem. So I have 1,500, and I'm going to subtract 29.5. Okay, again, I'm going to circle my uncertain digit. In this case, it's the 5. And in this case, it's this 5. And remember, we can only have one uncertain digit in our answer. Okay, so when I go ahead and write out my answer, I end up with 1,470.5. Now I'm going to circle my uncertain digits. This 5 is uncertain, and it turns out that this 4 is going to be uncertain because it lines up with the 5. Okay, I can only have one uncertain digit. That means everything here has to go. So that means that my answer is going to be 1,400, or if I round up, because it's 1,470, I get 1,500. Now, I know this doesn't make any sense, does it? How can you end up with the same number after subtracting something? Well, you got to remember that this 1,500, that 5 was guessed at. What if it was 1,600? What if it were 1,400? Okay, does subtracting 30 from any number that uncertain matter? No, it doesn't. Okay, now I will say this. In the real world, when you're making measurements, you're never going to be measuring something with that type of precision. You're always going to have 2 or 3 digits after the decimal place because we can measure very, very precisely. So in the grand scheme of things, you're probably never going to have a measurement of something like 1,500 where you have to guess the 5. It could be, though, that you're working with really, really, really big things or large amounts of fluids or something like that. If you're looking at some type of a container that's holding liquids that you're measuring, and if you're talking about gallons and gallons, 30 gallons versus 1,500 is not really going to make a difference in the grand scheme of things. So you got to kind of take it the way it is. 1,500 is a large number, 30 isn't. And if that 5 is uncertain, if it could be a 6 or a 4, that can change the number to the point where it does fall between that 1,400 and 1,500. Okay, so just keep that in mind. Another thing is you could write the 1,500 in scientific notation, write the 29.5 in scientific notation, and then subtract them that way. And you can definitely see then that you would end up with either 1.4 times 10 to the 3 or 1.5 times 10 to the 3. Okay, so now what we're going to do, is we're going to go ahead and look at multiplying and dividing. Multiplying and dividing numbers with significant digits is really, really easy. Because you're looking at the total number, and you're looking at which one has the least number of sig figs, and that's what you end up with your answer. So multiplying and dividing is really, really easy. It's adding and subtracting that's really, really hard. Okay, so here we have 20.5 times 4. So what I'm going to do is I'm going to type it out, 20.5, and then I'm going to have times 4. And then what I'm also going to do, again, is I'm going to circle my uncertain digits. Now, if I multiply by an uncertain digit, whatever I get is uncertain. Okay, so when I multiply these two together, I end up getting, let's type this out, I end up getting 82.0. Okay, now notice that when I do this, this is uncertain when it multiplies by everything, and then this 5 is uncertain. Okay, so the first time I go through, it ends up being like this. Every number, oops, every number I multiplied is uncertain, isn't it? Because I multiplied by 4. 4 times 5 is uncertain. 4 times 0 is uncertain. 4 times 2 is uncertain. Okay? So I end up with all of the digits uncertain. So what does that make my answer? 80. Or you can write it out as 8.0 times 10 to the, let's see, here we go, 10 to the 1 power. Okay? I know, it's crazy, isn't it? But look at the rule. The rule is least number total. This has 3 sig figs, this has 1. Our answer can only have 1 sig fig. Oops, this is a mistake. Let me fix this. It has to be 8 times 10 to the 1 because you can only have 1 sig fig. Okay, what about 15,000 times 15? I'm not going to do the circling for this one, but if you look at this, you take 15,000, divide it by 15, and you're going to get 1,000. How many sig figs should that have, though? That's right, it should have 2 sig figs, but I have 1,000. How am I going to do this? Well, there's several things you can do. You can type in 1.0 times 10 to the 3. So that's one way of writing it. Or what you can do is you can write down 1,000. Oops, let me fix this. You can write down 1,000, and then this is a little trick. You can put a bar over the 0, and that tells you that that 0 is significant. Okay, so there's 2 different ways to do this. If you have any questions about significant digits or you need some practice, let me know. I have some worksheets that I can go ahead and give you. So just let me know in class whether you need some help, or leave me a note on Edmodo. That's probably better. And then I can go ahead and provide you with some worksheets that you can do to practice. Okay, so now what we're going to do is we're going to talk about scientific notation. Hopefully you remember that scientific notation takes the form of m times 10 to the n, and we've already been showing that a little bit in our significant digit review. Okay, m is a number that is in between 1 and 10 for scientific notation. If you're using engineering notation, the power of n must be a multiple of 3, or it can be -2. So when we talk about engineering notation, we're using powers of 3 just like the metric system. Okay, so if I have the number 75,300, I'm going to move the decimal point to the left. When you move the decimal point to the left, you use a positive exponent, because you're really taking 7.53 and multiplying it by 10 times 10 times 10 times 10. And what's 10 times 10 times 10 times 10? It's 10 to the 4th power. So you move the decimal to the left, you get a positive exponent. If I have the number 0.000357, I'm going to move my decimal point to the right. The number is getting smaller. It is a smaller and small number that's getting larger. And that means that I'm actually taking 3.57 and dividing it by 10 times 10 times 10 times 10. So really what I'm doing is I'm taking 3.57 and I'm multiplying by 10 to the minus 4, or I'm dividing by 10 to the 4. And remember, when you divide by a power, you just end up subtracting that power. So when we move the decimal to the right, we're going to have a negative exponent for the number of places we move it. So all numbers, let's do this. All numbers with zeros for placement purposes only must be written in scientific notation to remove any confusion about whether zeros are significant or not. So for me, I like writing my numbers in scientific notation if I can. If there's zeros at the end of the number or at the beginning of the number with a decimal point, so I can make sure I know how many sig figs I have. So for instance, if I have 450, I would write that in scientific notation. 0.034, I'll write it in scientific notation. 100, I would write that in scientific notation. It's just easy to determine your sig figs when you write these numbers in scientific notation. Okay, so for instance, if I have a number like 1,505, which you see right here, you can leave that alone. Okay? If I have 0.137, I can leave that alone. Unless, of course, this 1,505 only has 3 sig figs. Then you should write it in scientific notation. In fact, you have to. Because otherwise you'd have to put a line over the 0 and get rid of the 5. Okay? So it's always easier to just write the number in scientific notation. So any number greater than 10 or any number less than 1, write it in scientific notation, and that clears up everything. The only time you won't do that is when we do circuits, but every other thing we should do that. Okay, one thing that I do need to cover with all of you is that we will be working in what we call the MKS system. That means that all of our measurements have to be in meters, kilograms, or seconds, or they have to be in some combination of meters, kilograms, and seconds. Okay, so if you're given a measurement in grams, or if you measure something in grams, you have to convert it to kilograms. If we make a measurement in centimeters or millimeters, we need to convert it to meters before we can put it into a physics formula. Okay, that's the trick right there, the physics formula. Okay, if you are collecting data and you're analyzing data and you're looking for patterns, if you're not worried about whether your constant matches a known constant, you don't really need to worry about this conversion thing. But I would say, just to be safe, if you've never taken a physics class before, I would say make sure everything's in meters, kilograms, and seconds. So what if in a problem you're given kilometers per hour? What should you do? Yes, you should convert it to meters per second. Okay, so meters, kilograms, seconds. And every unit I give you, I will give you in MKS, or derived units in MKS. Okay, so what are the metric prefixes to help you out here? We work with a lot of metric prefixes, but we do not work with King Henry died by drinking chocolate milk. Okay, we don't do it. We don't have Henry, we don't have died, and we don't have drinking. I don't use deca, deci, or hecto. The only time I have ever seen those 3 is when we teach it in our lecture notes, or professors have it in a lab, a math lab, at the beginning of a semester of physics, and then you never see them again. Nobody ever uses them. And if they do, you know what? You can look it up on the internet. But for this case, what we use the most are the following prefixes. So let me show you this. Okay, so we mainly use tera, giga, mega, kilo. Now, tera, giga, and mega are basically used in electronics and when we're talking about disk size. Terabytes, gigabytes, megabytes, those are all sizes based on your data storage. Okay, so that's why I put them in here. Kilo, we use kilometers, and we use kilograms, so kilo is pretty popular. We also use centi and milli on our meter sticks. Micro, we use micro, nano when we're talking about wavelengths. Pico and femto when we're talking about really small times, and when we're talking about capacitors. Okay, so these are the prefixes that we use. You need to have them memorized. Okay, they may show up on your formula sheet, maybe, maybe not, I'm not sure, probably, but why waste your time looking it up if you can just have it memorized? So here's the mnemonic I use. Actually, my students made this up for me because I really am horrible at making these things up. So here we got Tom got mad, killed cheating married man, near pretty females. Okay, Tom, tera, got, giga, and so on and so on. Notice you only have to memorize 2, and everything else you count by 3. So we know that kilo is 10 to the 3. We know centi is 10 to the minus 2. Then you go by 3s. If you go smaller, it's by 3s. So -3, -6, -9, -12, -15. If you go larger, it goes 3, 6, 9, 12. If you have trouble counting by 3s, I recommend that you get, here, I'll even write it down for you. Schoolhouse Rock. And it is 3 is a magic number. Okay? If you have any trouble counting by 3s, you need to go onto the internet, and YouTube, I'm pretty sure will have it, and you need to go ahead and get yourself some Schoolhouse Rock here. Here, I'm going to change the color so you can see it. Actually, there we go. Okay, Schoolhouse Rock, 3 is a magic number. And they count by 3s, and it's a really great song, and you'll be singing it all night long if you play it. And if you come in and sing it for me, I'll give you extra credit. So there you go. Schoolhouse Rock, 3 is a magic number. Okay, this is a lot of words, isn't it? Okay, so for unit conversion and all calculations, you have to write down your units explicitly. One of the things that they're going to nail you on the AP exam is if you put numbers into a formula and you don't have any units. The other reason you need the units is to make sure that you're in MKS. If you just put the numbers in, then you're not really paying attention to what you're putting into the formula, and you could end up with the wrong answer simply because you use grams instead of kilograms. When you're doing any calculation, you treat the number or the units as algebraic quantities. So you multiply numerators, you can multiply denominators, you can cross multiply, you can eliminate identical units by dividing. All of those things can be done with units. You're going to use the conversion factors that are found in the textbook for the internet. I do not go over English conversions because in physics we just do the metric system. We don't work in English units or British units, whatever you want to call them. Okay, so basically when we do conversions, we're really converting from like kilometers per hour to meters per second. We're not really converting from miles to meters or miles to kilometers. Okay, so whenever you do a conversion, you're multiplying by the number 1, or you're dividing by the number 1. That's it. So what we do is we make the conversion factor equal to 1, and then you can multiply any number by 1 and get that number. Okay, we're going to check to see if our calculations are correct by looking at the units. and making sure that the units are the correct units for our answer. So one of the things we're going to do is make sure that when we're doing our calculations that we're actually getting the correct answer by using the units, and we call that dimensional analysis. Now, here's the trick. Only quantities that have the same units can be added and subtracted. Same thing with vectors. You can only add vectors when they're in the same or anti-parallel direction. Okay, so vectors must be parallel or anti-parallel to add them. You can add them when they're perpendicular, but not numerically. You have to use Pythagorean theorem and arctangent. Okay, so here's an example. We have 1 kilogram equals 1,000 grams. If I divide both sides by 1,000 grams, I get 1. And that's equal to 1 kilogram over 1,000 grams. If I divide both sides by 1 kilogram, I end up with 1,000 grams over 1 kilogram. It's all equal to 1. So now what we're going to do is we're going to do some conversions. So here I have 15 kilometers and I want meters. Okay, so what I'm going to do is I'm going to take my 15 kilometers, and I know that 1 kilometer, and I'm going to put that down here because I want to get rid of it, is equal to 1,000 meters. How do I know that? I memorized my metric prefixes right here. Kilo. Kilo is 10 to the 3. That's 1,000. Okay? So now when I multiply these two together, now you may be asking, wait a minute, Dr. H, why did you put 1,000 on the top and the kilometers in the bottom? Well, I want meters and I want to get rid of kilometers. So remember, the units have to cancel out. So whatever you want, you put on the top, if that's where you want it, and whatever you want to get rid of, you put it in the diagonal. Okay, so notice it's diagonal. So here's your diagonal, and it cancels out. Okay, so I end up with 15 times 10 to the 3 meters. Could I have done this an easier way? Yeah, look at this. Kilo is 10 to the 3. I could have just immediately written this answer down. Okay, so kilo is 10 to the 3. Same thing here, I could do this for pico. Look at pico. What is pico? Pico is 10 to the minus 12. See right there, 10 to the minus 12. So I could actually write this next one as 250 point times 10 to the minus 12 seconds. Done. Now you may be saying, don't I have to write that in scientific notation? You should, okay? And so that's going to be 2.50 times 10 to the minus 10 seconds. And this is going to be 1.5 times 10 to the 4 meters. Okay? Now, here we get a little tricky. How do we do this one? We have kilometers and hours, and we want meters per second. So let me show you how to do this one. We're going to take the 55 kilometers, and then what I'm going to do is I'm going to do 2 fence posts. I don't know if that's what you call these things. That's what I call them, because it looks like a fence. Okay, and what I'm going to do in the bottom here is I'm going to put 1 hour. Okay, 55 kilometers divided by 1 hour is 55 kilometers per hour. Okay, now what I need to do is I need to convert my kilometers to meters. So I'm going to do that right here. I want meters in the top, so I have 1,000 meters. And I want kilometers in the bottom, so I have 1 kilometer. And now here I want seconds in the bottom. So there's 3,600 seconds in 1 hour. Okay, notice the crisscross. Okay, crisscross. Cross out. Cross out. Okay, now you multiply the tops and divide by the bottoms. So let's see what we get. We end up with, typing this out, we end up with 55,000 divided by 3,600. Okay, and so let's go ahead and put that in your calculator. You probably can do that in your head. I can't, so I'm not going to. So 55,000 divided by 3,600 gives me 15.2. So my answer, I need the same number of sig figs as what I started with. So I'm going to put 15 meters per second. So 55 kilometers per hour is equal to 15 meters per second. Is that cool or what? It's very cool. Okay. So there you go. That's your conversion. Now you may be saying, wait a minute. Couldn't I just take the number and divide by 3.6? Yes, you can. Because notice here, I've got these 3 zeros here. I could get rid of those, right? I can get rid of these 3 zeros, and I can put a decimal point there and get rid of these 2. And now I have the number divided by 3.6. So now you know, easy speasy, what your conversion from kilometers per hour to meters per second is. You just divide the number by 3.6. And there you go. You've got it. Okay. For dimensional analysis, I know this has been a long lecture, but you're hanging with me, I'm sure of it. Okay, so for dimensional analysis, what we're going to do is we're going to put the units into the equation to see if they equal each other. So the units for speed are meters per second. So we're going to put meters per second, and we're going to put a question mark here. Are they equal? And we're going to take meters times the seconds. Well, does a meter per second equal meter times seconds? No, they're not equal. So what does that mean? It means your formula isn't correct. Please, please, please check your formulas. You would not believe how many students have lost points on their AP exams because they wrote the formula down quickly, thinking they knew what they were doing. They didn't put the units in. They didn't multiply the units and check their work. I know it seems like a lot more time to do that, but it's better for you to invest 5 extra minutes into checking your work than it is for you to lose the points because you rushed through it and you didn't check your units. Do you have to do this every single time? No, but when you put the numbers into the formula, you should be able to tell. So if I have something like 15 meters times 2 seconds, my mouse is getting jumpy. What does that give me? It gives me 30 meters seconds. Okay, that doesn't make sense. So I'd be like, what? What happened here? It's wrong. Okay? So make sure that you're checking your units and making sure that the units you're multiplying actually come out. Another thing that you can check is make sure you're actually doing the square root in your calculator. There's a lot of times students give me an answer and it's wrong because they didn't actually follow through and do the square root to get the final answer. Okay, so that's it. That is the end of the math review. If you have any questions at all about the lecture notes, please see me. If you think that you need some practice in some of these things, please let me know, and I will make sure that I either post a worksheet for you to do or I'll provide you one in class. Okay, thanks so much for listening.